So in this fourth lesson, we're going to take a look at some polynomial theorems. And we're going to start with a very important one called the fundamental theorem of algebra. And it says if you have p of x as a polynomial of degree n greater than 1, then p of x, meaning polynomial function, that's why they use a p, has exactly n roots, including multiplicity and its complex roots. So let's kind of decode that. What is that talking about? Well, the most basic polynomial is a horizontal line y equals 2. It's a constant monomial. It has no roots. Why? It has a degree of 0. That's why this theorem says it has to be greater than or equal to 1. But as soon as I put an x here, this has a degree of 1, and that means that it's going to cross the x-axis at exactly one place, and this right here is the root or the 0. Now, if I change this to a square, right, if I change this to a square, then I have a quadratic, and that quadratic would look like this. And yes, this one only touches it once, but as we know, we could put a minus, I don't know, minus 2 here, and then all of a sudden it's below the x-axis and it's touching it now 2 times. And so it says you have exactly n roots if you include multiplicity. Well, the original problem I had there had a multiplicity of 2 at the origin because it was a double root at the origin. And the complex roots would show up more likely, they could show up with a quadratic because you know it can't cross the x-axis, but I'll give you a very good example of one from a previous unit in Unit 2. If you had y equals x to the 3rd power, okay, and you said plus 2, well, that would graph, remember you would move your vertex up to 2, you would draw your cube, and according to the fundamental theorem of algebra, there should be 3 answers. I only see 1, and the reason I only see 1 is there's actually 2 complex answers. And so notice what it says, it will equal this number if you include complex roots and real roots and any double or triple roots. So a way to sum this up is the sum of all the roots that you could possibly have equals the degree of the polynomial. That's what it is in just kind of layman's terms. So we have a corollary to that that says when using the fundamental theorem of algebra, all the complex roots have to come in pairs. Like, how did I know there were 2? Why isn't there just 1? And the reason is you get a complex answer by taking the square root of a negative. But when you take the square root, there's a plus or minus, which means when solving, it's always plus or minus some I. So if somebody gives you a problem and says, hey, there's a root of x equals 3i, please find the rest of the roots, you get negative 3i for free if you know this corollary. So that's really good. If there's only 3 possible roots, I just found 2 of them. All right, so if I take a look at the next theorem, I actually combined, traditionally, these are actually 2 separate ones. I put them together. And basically what it is it's a theorem about roots and factors within polynomials. So for any real number r is a root of a polynomial of f of x if and only if the following 4 things are true. So the first thing is r is a solution to the equation f of x equals 0. And that's basically just the definition. If I call something a root or a 0, that means that the polynomial will be solved to become 0 at that value. Basically, it means that I factored it, I set them equal to 0, and I found it to be an answer. Okay? So let's say that answer is r. Well, then if r is an x-intercept, I would then write it as r comma 0 in a parentheses to indicate that it's an x-intercept, as we've learned in previous chapters. Well, that r could then be written as a factor because it had to come from a factor, and that factor would be x minus r. Please keep in mind you change the sign of r from root to factor or factor to root. So whatever this is, this will be the opposite. Let me give you an example of that. So let's say we had, as an example, let's say one of my zeros was x equals 2. Well, my x-intercept would be 2 comma 0, and the factor that produced both of these is actually x minus 2, okay? And of course, if I used a negative number, right, so let's just go back and rewind this for a minute, and let's say I started with x equals negative 4, well, then my x-intercept would still be negative 4, it's just another way of writing the answer, but the factor that produced it would be x plus 4. All right, and then these are all things we've been learning since quadratic, so this shouldn't be a big deal. It also applies to other polynomials because keep in mind a quadratic is a type of polynomial. But then here, the last one is very specific to the polynomial chapter, and it says if f of x is divided by x minus r, meaning if I divide by this factor, if I use long division, or if I use x equals -4 for synthetic division, the remainder is always equal to 0. Meaning, if I do long division with x plus 4, my earlier example, and I do long division, then I do all this work, blah, 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 and I get 0 at the bottom. Or if I did synthetic division, and I used x equals -4 out here, of course, we would just put a -4 there. So if I put a -4 out there, I would do all this work, blah, 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 and I would get a 0 here. Now, that's a pretty powerful thing to know that you'd get a 0 here and a 0 here, either if you use the factor or the root. Why is that so important? Because this allows me to factor. And the conclusion is that the divisor, the thing I divided by, as well as the quotient, the thing that would be up here, or with synthetic division, the thing that would be down here, they are factors of the original problem. So the conclusion here is, which is really interesting, is that factoring is the universal way to factor any polynomial, including a quadratic, which is very interesting. A corollary to that is the remainder is always equivalent to direct substitution, right? So if this is true, then this would mean that if I put in r, I would get 0. But it's also true if it doesn't come out to 0. So like, let's say somebody asked you to find f of 3, right? And you put a 3 here and you did synthetic division, then whatever this number is, that's what f of 3 is. Blah, 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 blah. You get 11, then f of 3 is actually equal to 11. So that's a lot of talking. Why don't we look at some examples? Most students understand this better when you see concrete examples. So that's what we'll do next.